Welcome to this meeting of the IARPA Coastal Resilience Community of Practice. I'm Christina Bonsell. I'm a marine ecologist with the Bureau of Ocean Energy Management based in Anchorage, Dena'ina Homelands. And I'm one of the co-leads for this team, along with Taze Jones, who's with the Fish and Wildlife Service, Tom Ravens at UAA, and Liz Walsh with the Scott Polar Research Institute. Our team focuses on strengthening coastal community resilience and advancing stewardship of coastal and natural, or of cultural and natural resources, particularly by engaging in research related to the interconnections of people, natural and built environments. We hold multiple webinars each year and connect with other groups and the broader work in IARPIC as well. So for this meeting, I'm really bad at coming up with titles. And for this meeting's title, I kind of wanted to do a riff on where the rubber meets the road, like where the ice meets the sand or something like that. But I didn't quite get there. But generally, we wanted to convene a meeting to highlight how coastal processes outside of permafrost thaw and wave and tide-driven coastline erosion need to be considered when thinking about natural hazards and Arctic coastal resilience. Coastal science and coastal resilience are innately interdisciplinary, and so today's meeting really highlights that by bringing together sea ice and oceanography, sediment transport, and engineering considerations. So for our speakers today, we have Dr. Emily Eidam, who's an associate professor at Oregon State University. Her research focuses on the transport of sediment through riverine and coastal environments, and she'll be talking about her work mapping the nearshore seabed and sediment reworking in Harrison Bay in the Beaufort Sea. And then after Emily, we'll have Craig Leidersdorf, who's a coastal engineer and co-founder of Coastal Frontiers Corporation. Craig has a great wealth of experience and expertise in shore protection and coastal processes in the U.S. Arctic, and he'll be talking about some work and some data his group has collected on ice pileup, ride-up, and encroachment in the Alaskan Arctic. So Emily will go first, and then we'll have some time for questions, and then Craig will go. We'll have some time for questions, and then further discussion. Hopefully with this big of group, we'll have some good discussion and time for that. So with that, I will hand it over to Emily.
Thanks, Christina. Let me set up the screen share here. Can you guys see the big slide?
Yes.
Perfect. All right. Well, I really appreciate the invite to come and chat today, and I'm also excited to be paired with Craig, and hopefully we can kind of give you a full picture of ice reworking processes offshore and then onshore. So this should be fun. So I'm a marine geologist, and I care about modern transport of sediments from rivers to continental shelves and slopes. And I really like continental shelves because during the present high stand in sea level, in many places, these are sites where sediment is stored and accumulated, and it forms interesting sedimentary records, and it also sequesters nutrients like carbon, which we're pretty interested in today. This is an old figure that is an example from the Washington-Oregon margin near where I live. And the gray zone is a big muddy depot center, site of deposition of mud offshore the Columbia River. But there's other mud belts that are formed from smaller rivers and bluff erosion. So if we sort of take this framework and start looking at the Arctic and thinking about sediment sequestration on continental shelves there, we can't ignore the fact that sediment loads to the Arctic are increasing. So this could be a pretty interesting place to think about shelf sediment storage. And a lot of that increase is coming from coastal bluff erosion of permafrost-rich coastlines. There has been suggestions that Arctic river sediment discharge is increasing as well, although that's the topic of a little bit of debate. But this really begs the question of what is happening to sediment storage on Arctic shelves. And another important question is, do we even have a good baseline for looking at changes? We know that the wave climate's changing. We don't have a lot of existing data about sediment accumulation. So this area is pretty ripe for research. So I've been working on and leading a collaborative project funded by NSF for the last several years to try to track sediment transport through the Harrison Bay portion of the Beaufort Shelf. This area is near Cape Halkett, where there's pretty rapid coastal erosion, but it's also backed by the Colville Delta, which is a source of sediment. So it's a pretty dynamic area as far as sediment transport. And we had a lot of research questions. We wanted to map seabed features and sediment types, update some maps that were generated in the 80s. And we wanted to think about rates and pathways of sediment dispersal through the open water period. So is sediment getting delivered to a depicenter, or is it bypassing this shelf and going off into the Arctic Basin? We also looked at geotechnical properties. That was work led by my colleague Nina Stark at Virginia Tech, now at University of Florida. And we did some modeling in Delft 3D to think about how the shape of the shelf might change and how deltas like the Colville Delta might change over the next 100 years or more as waves become more energetic and as sea ice retreats. We collected a large suite of observational data, shown at right, and much of this data is online now, and the rest is going to be uploaded in the next few months. So for purposes of this talk, I wanted to just zoom in and focus on a couple aspects of this work, which are keel scours in the spirit of the theme of hazards, as well as some other interesting seabed features. And then I want to think more broadly about the topic of seabed erosion over multiple decades. So I suspect this group is pretty familiar with the concept of keel scours, but to quickly recap, there's sort of two very general types of sea ice in the Arctic. There's land-fast or shore-fast ice that tends to grow attached to the shore in the fall. This is somewhat thinner ice, and you can see it here in a nice radar image collected during Jim Thompson's CODA project from Skuliak. And this is pack ice forming offshore, and as this grows toward the coast, it grows southward, it'll eventually meet this land-fast ice, and it will collide and form big pressure ridges, like this impressive pressure ridge, and those develop submarine keels, ice keels, that gouge the seafloor, because even during winter, the ice is still a little bit mobile. It's pushed around by winds and currents. And it tends to rework the seabed in this area called the Stumaki zone. I love that term. And that zone is, typically ascribed to about the 20 to 40 meter water depth, but it can vary. And that's just based on the depth where these keels run into the seafloor and drag across it and disturb everything. This is a multi-beam image we generated of the seabed at a mid-shelf depth. This is a couple 100-meter scale, and you can see the whole seabed has been disturbed. So as a marine geologist, this is both fascinating and deeply troubling, because this makes it hard for us to apply some of our typical methods for understanding sediment deposition. There are complex cross-cutting relationships. There's a complex history of Asia scours here that would be difficult to unravel. And from a geotechnical perspective, these scours are interesting because there might be soft sediment infilling these that has been recently deposited through suspension settling and bedload transport. But sometimes the bottom of these scours contain very compacted, indurated, very stiff mud. And that could be a result of either sediments getting mashed down as the ice is going over them, or they could be stripping away newer, higher porosity sediment and exposing older, more compacted, more dewatered sediment. So we were able to collect over 600 kilometers of multi-beam trackline data from the RV Ukpik, so a 45-foot coastal vessel, in 2021 and 2022. And we tiled this into 100-meter grids, and I worked with a really great undergraduate researcher here, Riley Smith, who was intrepid enough to go through all of these tiles and manually classify them into different seabed types. So they've been classified into areas of smooth seabed where we don't see any features, areas of dense keel scour, and I'll give an example in a moment, areas of very sparse keel scours where we might just see one or two in a grid cell. Something that we're calling hard pan substrates, which is a little bit strange and mysterious, and then strudel scours or pits. So I just want to walk through and show maps of where we find these features. Smooth seabed, if you look at things on the 100-meter scale, this is pretty ubiquitous. I think this just highlights the real diversity of features here. Anywhere you go, you can find areas where you don't see a lot of features, but you also see features everywhere. So this is the map of dense keel scours. And these are areas where pretty much the whole 100-meter tile is full of some sort of scouring evidence. The densest scours that we saw were on top of Weller Bank. And the bathymetry I'm showing here is contoured IBCO bathymetry. Admittedly, it's not great. Weller Bank doesn't show up as prominently in the IBCO data set as it probably should. We've driven over it and it has a prominence of about 12 meters water depth. So it's not surprising that these pressure ridges would be getting hung up there and causing pretty intense scouring. There's also very dense scouring offshore of Cape Halkett, and that also makes sense because this is an area where some of the ice might be getting squeezed as it goes around the Cape, and you might get more vigorous seabed disturbance. These scours have pretty large geometries. If you draw a transect through them, you can see depths of 0.5 meter up to 1.5 meters. As someone who usually thinks about seabed disturbance on the scale of bioturbation, so maybe 10 centimeters, this is huge, right? Sometimes we might only collect a 1 meter long core and that's all we need in Oregon, but when you go here, the scale of mixing is just phenomenal. Scour widths are usually about 10 to 40 meters if you're looking at the really big ones. And I love this example. It looks like 2 scours, but it's actually just one that has a very complex geometry. And sometimes there are little ridges piled up on the sides of them, which are kind of fascinating. I know Jim Thompson was out here diving looking for a mooring, and he said they couldn't see anything. They could just feel piles of dirt on the seafloor. And I think that there are these little ridges. Like if you plow a field, you make a ridge on either side of the trough. Sparse keel scours are what we defined when we only found 1 or 2 scours in a 100-meter area. These are often smaller, and you'll notice that we see some of these in shallower waters where we don't necessarily see the very dense keel scours. And the way we classify these, they tend to be a little bit smaller. They're on the order of 20 centimeters deep and 2 meters wide. But again, in my world, 20 centimeters is still quite a lot of physical disturbance. Then we saw a lot of substrate that was just very difficult to classify. We're calling these hard pan substrates, and I think that these could be generated by ice scouring, but they often tend to have a little bit more pattern to them, which is a little bit strange. I kind of have a hard time explaining this. Anecdotally, I was talking to Bill Coplin once, who's the former owner of the Ukpik business, and he described diving down and finding areas of seabed where it was muddy, but you can't dig a shovel into it. It's just very consolidated. It's not frozen, it's just very stiff. Those might be outcrops of relict Pleistocene clays from the Gubic Formation. They might be sediments that have been impacted by ice. We also noticed when we put a GoPro on an instrument and dropped it on a seabed, we found similar areas of mud where normally it would create a big plume of mud, but nothing happens. You just drop an instrument on the seabed and it's very solid. In rivers, we see substrates like this where you have old outcrops of clay on the riverbed and the water actually plucks little mud clasts out of it. We call those rip-up clasts in geology. I suspect that some of these could be thought of as akin to rip-up clasts where maybe there's been plucking action, perhaps by wave energy. Or perhaps it's related to anchor ice formation. There have been a lot of descriptions, especially by some of the USGS researchers, about finding anchor ice nucleating on the seabed, especially in areas where there is some fresh groundwater coming out from the landscape. And if the anchor ice pillows become large enough, they can break free and raft to the surface. These are examples from other areas where anchor ice is forming on gravel substrates, but there has been direct evidence that these form on the finer substrates in the Harrison Bay area. So maybe these represent that sort of plucking. It's still a little strange that there's so much pattern to them if that were the process happening. We also found evidence of strudel scours and pits. Strudel scours are often associated with places where the river overflow floods the ice in the spring, and then it dives down to the bed through cracks and holes in the ice. And some of the best images on the web for this are from coastal frontiers. There's areas where they've worked near some of the oil developments, and they've captured images of the Colville plume. Water is sort of diving down through holes in the ice, and then it jets out a pit on the seabed. We did find pitted features elsewhere, not near the Colville. I don't know if those are just pits created by smaller discrete pieces of ice dragging on the bed, or if there's some sort of overflow in this area. That seems a little bit unlikely. So if you put all these features together, you get a really messy map, and I have not found a great color arrangement to make this map look better. But the main takeaway here is that most of the map is red and orange. So the seabed features are very dominated by keel scours, which is not too surprising. The blue line here is the far north fiber optic cable that was severed somewhere on the shelf about a year and a half ago. So it's not terribly surprising. This is an area of a lot of keel scour activity. Hopefully, as a community, we'll move toward having a nice hazard map for northern Alaska if it's not already in the works. There's a lot of data that could go into it at this point. I was a little surprised to see keel scours at such shallow depths, and I was plotting up the landfast ice extents. Hayo Aiken and Andy Mahoney and others had digitized those extents from satellite images. The data set I grabbed was 96 to 2003. Andy says they've since updated it. And it's good to know where that ice edge is, because presumably that's where your pressure ridges form, and that's where you'd expect the most scouring. If you look at it in December, those areas are typically sitting on the middle shelf, so kind of in that 20 to 40 meter zone that we typically associate with the Stamiki zone, and then it just progresses further seaward some years until May. But for these scours that are farther inshore, they're probably not a result of that Stamiki zone and those big pressure ridges. And I was chatting with Andy this week, and he reminded me that a lot of those shallower scours might be forming during breakup when there's a lot of ice that's mobile. So we also worked to do some quantification of these scours, and Jaap Nienhuis led this effort together with his grad student, Nico Kaloris. And they took the 600 kilometers of multi-beam data, gridded it at 8 centimeter resolution, and split it into 200 meter tiles, and then manually classified 67 of those tiles as a training data set, and then applied this MMSI tool to try to ID scours and did some tuning. And the full details of that are available in Nico's thesis, and we're trying to get them formally published in a separate paper at this point. They detected 36,000 scours. We could convert those into an along track density to compare to similar previous work, although I'd be a little nervous doing that because some of these scours might represent the same scour across multiple tiles, but that's still a lot of scours. This is a map they made of the orientation of scours that they detected, and I think this is really interesting because the red zone over off of Cape Halkett and this blue zone on the middle shelf both show dominant orientations in the along shelf direction. So once these pressure ridges form, it seems like there are forces sort of pushing that ice along shore, parallel to the shelf isobaths. But in these shallower zones, the green zones, the scours are oriented more across shelf. And so again, it might represent those scours forming more during the process of spring breakup when that ice is starting to move seaward rather than along the shelf. But maybe worth investigating more. They also calculated scour density, which is the fraction of seabed area scoured in a tile. And they didn't find a density of more than 5% in any area. I think this is pretty conservative. And I think the issue is that the detection algorithm is picking up, new scours that have prominent relief and possibly ignoring a lot of the old scours underneath that. So it might be interesting to try to tune this. We've also debated ways to try to age scours. I think we could get relative ages by looking at the rugosity or the roughness of the seabed within a given tile. Exact aging is tough, and that's another story about lead 210 that we've explored a little bit. So they were also able to take their results and plot the surface density versus water depth, and then the scour width versus water depth. And this is kind of interesting. The highest densities of scours occur kind of in this classic Stamiki zone of 20 meters onward, but you also see a high density very near shore. So that's probably a lot of that springtime breakup ice that is scouring out. The width is generally correlated with water depth up to some limit. It seems like there's a maximum limit of sort of this 17 meter average value. They don't get a whole lot wider than that, presumably just because of the geometry of how the pressure ridges pile up. So we also have some detailed geotechnical data across these. Nina Stark's group uses a free fall penetrometer that they developed. They did over 1,000 casts here in the 2 years that we were surveying. And they usually go and collect 5 drops at a station in a coastal environment just for repeatability. But if they do 5 drops at a site here, typically every single one of those 5 profiles will be completely different from each other. So there's extreme variability in the seabed, which is not hard to imagine when you look at the keel scour maps. And Nina is working on a detailed picture of how the geotechnical properties change across a single scour. But she recently moved institutions to Florida and has been a little busy with the hurricane cleanup this week. So stay tuned for those results. They're pretty cool. Finally, I just want to touch on seabed erosion. Scours are a known hazard to buried seabed infrastructure, but I think that there's another hazard if you think over long time scales, which is just gradual erosion in the shelf. And we were motivated to look at this in part by work by Erk Reimnitz and others in the 80s. I love these figures. They were thinking broadly, and they've got a map of Cape Halkett here where they're sort of trying to imagine where the shoreline was 1,000 years ago and where it will be in 1,000 years. And I suspect that this is a little conservative based on current erosion rates. But if you look at that in a profile view, Erk put forth this idea, which is kind of fundamental to coastal geomorphology, which is as the shoreline erodes, the shelf should effectively follow it. So if you have rapid shoreline retreat, and if you assume that the shelf maintains its slopes, maintains its profile shape, the whole shelf should be backstepping. It should be retreating to follow the coastline. And because most continental shelves have a concave up profile, like a bowl, sort of, that means that the highest rates of vertical erosion at any place should be on the inner shelf or in the nearshore zone, because that's where you have the steepest slopes. And he has this semi-quantitative figure. I should make more figures like this with polar and kayaks in them. And he used seabed bathymetry that they measured in 1980, and then based on shoreline retreat rates, made a prediction of where the seabed should be in 2080 if the shelf follows the shoreline in effect. So we were interested in trying to do some bathymetric differencing using our new data. And thankfully, Zimmerman and others took some NOAA charts from the 50s, and they were able to correct those and update some datum issues. And then they did comparisons to newer multi-beam data. And I think Mark might be on the call, so we really appreciate this data set. And they found that there are areas, these orange and red dots, where there has been on the scale of 1 meter of seabed erosion since the 50s. So we applied a similar method to our trackline data. And the gray data are areas where we don't feel confident in the difference. But outside of that, there are a few light blue areas on the middle shelf where there's probably a little bit of modern sediment deposition. Certainly not as much as on other like West Coast shelves. But there are these red hotspots of erosion. And there's a big hotspot over by Cape Halkett where there has been up to 3 meters of erosion in the past 70 years. And there's also a big hotspot on the Colville Delta front. So there is a tiny submerged delta front. This is a compound delta, like some of the tropical deltas in shallow seas. And that steep front seems to be retreating, causing these large erosion rates. So my student digitized the Reimnitz figure and translated a little bit to overlay. We were just curious, and his prediction is great. What we've measured in 7 years change basically equals what he was predicting, but over a time scale of 100 years. And that makes sense since the shoreline retreat seems to be accelerating a little bit. So in terms of hazards, it's interesting to think about keel scours and seabed erosion, but also depending on the lifetime of the infrastructure, it seems like this vertical erosion of the seabed on the scale of 1 meter or more might be an important factor too, and is something to look into. So I'll wrap up there, and I just want to acknowledge all my wonderful collaborators. This has been a really fun team project, and we've had people specializing in the geotechnical aspects and the modeling, which I didn't really talk about, and a lot of other assistants getting preliminary data. And I'll just leave up this list of products for a moment. We've got some papers out, we've got some data sets published, and you're always welcome to reach out if you need PDFs or want links to more of that info. So thank you very much.
Thanks so much, Emily. Those figures were super interesting, and I would love to chat with you more about observations of scour. So we have, I want to take like a little bit of time for maybe one question for Emily before we go to Craig, and then we'll have more time for discussion at the end. So are there any quick questions for Emily? Tom.
So Emily, based on your research, can you answer one of the questions or the hypotheses that you put forward at the beginning? Like, where does all the sediment go? So are you seeing it being deposited, in the deep shelf, or is it going off the shelf?
Yeah, that's a great question, Tom. We did chase the lead-210 signal and found virtually none, except for a little bit right in the Colville Delta front, which I think was just the last year of deposition. That is going out to 20 meters water depth. So inshore 20 meters water depth, I don't think we can really say that there's a depicenter there over a century timescale. Based on mooring data, there is strong sediment convergence in the summer at that depth, which was also found on the Laptev shelf by the Wegner studies. But I don't think it's staying there for multiple decades. I think it's largely bypassing. Otherwise, even if we didn't find beautiful lead profiles, if they'd been mixed, I would still expect to find some excess lead inventory. So, Barnes put out an interesting idea a couple decades ago that maybe the shelf is net erosional and maybe all of that material is being removed through sea ice entrainment and ice rafting. And I think we're still trying to chase that and figure out if that could account for removal of everything. It's also possible that there is a little bit of a depicenter on the outer shelf, and we just don't have good enough cores yet to answer that.
Thank you.
Okay. Craig, are you ready to share screen?
I hope so. Let's try it.
Okay.
How about that? Have you got me?
Yep, got it.
Good. Thank you. Nice job, Emily. I appreciate your work. It's very insightful. And I think to mention Eric Reimnitz and the contributions he made over the years is very appropriate too. He was certainly a great scientist and a great collaborator. So I'd like to take us on shore now, moving from the near shore to the coast itself and talk about ice ride-up, pile-up, and encroachment in the Alaskan, Beaufort, and Chukchi seas. And I'll focus, since we're looking at resilience and infrastructure here, I'll try to focus to some extent on the engineering implications of these features. And while 20 minutes is a short time, and not to be discouraged by it, I'd like to cover 4 topics. First, provide you with an overview of the characteristics of these features and their significance for human activities. Look briefly at how they're formed, the conditions under which they form, and the seasonality that help us for planning our human activities. Thirdly, to summarize the historical data that we have in both the Beaufort and Chukchi seas off Alaska. And finally, to present you with our very rudimentary means of predicting encroachment, which is based on the use of the historical data we look at first under item 3, and then some assumed pileup geometry and the actual site geometry. So with that, let's forge ahead. I'd like to acknowledge here that U.S. Department of the Interior, BSEE, has been a major sponsor of our work, along with Shell Exploration and Production Company. And we acknowledge their support. And I also like to acknowledge a collaborator, Dr. Ken Vaudry, whom many of you may have run across. He's now in his 80s and still very active and involved, and actually compiled some of the early data on ride-up and pile-up and encroachment that we'll be looking at in this presentation. Pile-ups and ride-ups occur, by our definition, when moving ice impacts a fixed object, such as a natural shoreline, or a structure of anthropogenic origin. And if it fails in buckling, that's an out-of-plane failure, or bending as it moves ashore, forming a discrete pile of blocks. We call it a pile-up. Here's, if you will, a garden variety pile-up about 3 meters high, about 1 kilometer long. This formed northeast of Prudhoe Bay on Pole Island, which is one of the barrier islands that creates Stephenson Sound. And occasionally we run across more dramatic pileups, in this case 15 meters on Narwhal Island. This is also one of the barrier islands just to the west of Pole Island, not too far again from Prudhoe Bay. And you can see the magnitude here. It's overwhelming. It not only dwarfs those of us who were here, but the helicopter that brought us. If the ice remains intact or nearly intact as it moves ashore, then we refer to it as a ride-up. You see a good example here on, once again, on Pole Island. Notice this took place, the photo was taken in June, and it's primarily the ice is more ductile this time of year, and it moves on shore without basically fracturing into discrete blocks. And a more dramatic example, once again, a breakup. This occurred in Camden Bay, and it actually encroached onto the shoreline over 40 meters over a distance of more than 3 kilometers. So it was very impressive push on shore where the ice maintained its sheet-like integrity. A final definition of encroachment, which for our purposes, particularly for engineering purposes, is a horizontal distance that the ice moves past the waterline onto the subaerial slope. And this could be a natural beach, as we just saw a moment ago, or an engineered structure or shoreline. Perhaps the most dramatic example that I've seen occurred on North Star Production Island. This is about 5 miles northwest of Prudhoe Bay West Dock, 15 meters high with 24 meters of encroachment onto the island slope and up to this, if you can see here, this sheet pile wall that rings the work surface. This occurred in January 2008. And while the blocks are being cleared away here with mechanical excavation equipment, this pileup actually reached within about 50 centimeters of the top of the wall. And the combination of a wide, it's about a 20-meter wide bench, a 3-to-1 slope fronting that, and about a 7-meter wall, just barely contained this pileup as it was supposed to do. So I think this is pretty much the design 100-year event for this island. We've seen events of this magnitude several times in the 24 years that the structure has been in place. And so far, the system has worked. We've not had overtopping. And here's an example of a natural pileup, which we observed in the Chukchi Sea on Skull Cliff. This is about, it's between the Cuck River and Utqiagvik. Again, 15 meters high, 25-meter encroachment. And note that it not only crawled up this rather steep bluff, but actually encroached a bit on the tundra surface. And I think a common misperception we had initially is that a vertical wall would stop this type of feature from forming. In fact, the ice simply forms its own ramp as it rubbles against the wall or the cliff and then overtops it, as you see here. So how do we deal with this information from the standpoint of human facilities, of infrastructure? I think it's important both to consider these properties of encroachment for design and operations. If we can, site selection is by far the preferable choice. Let's just stay away from areas that are prone to encroachment. Failing the ability to do that, the next best is to create a setback distance or a buffer zone from the waterline that will accommodate the design encroachment event, as we saw with North Star Island. This could apply, as you see here on the right, to a structure. It could be a village. It could be an oil processing facility. It could be the shore crossing. Emily mentioned a fiber optic cable. The question here is, where do you daylight this, say, pipeline or fiber optic cable? How far inshore do you have to go before you bring it up out of the encroachment zone? So hence the need to try to predict the encroachment distances for design. Operationally, we can use the information on pileups and ride-ups in terms of seasonal constraints. For example, if we have a coastal storage pad or a dock, when do we need to vacate this facility and get out of harm's way during the season when these encroachment events can occur? And in a shorter term, if we have to have facilities on the coast, maybe it's a camp or a coastal construction site, can we develop a protocol for early warning and evacuation? And I think we can. I think you'll see that in a few moments. Imperfect, but better, far better than ignorance. And I'm sure Tom is well aware of this, but just to put this in perspective, the threat posed by encroachment is significant, but far less than that arising from direct ice loads on a structure. So, for example, the load created against a dock or an island by the ice canopy tends to be far in excess of the load posed by encroachment that has already pushed its way onto the shore, and in many cases is basically enforced by blocks rolling down the top of a pileup. how do they form? We were surprised that the primary drivers are quite simple here. The initial instinct was the harder the wind blows, the more pileups, the more write-ups we'll see, and that proved to be untrue. We need two things. We need a wind speed in excess of 15 knots, again, experientially, to energize the ice canopy. And we need to couple that with an abrupt change in wind direction here, which causes a loss of confinement. And the ice then can gather momentum, move in the opposite direction, and ride up or pile up against our fixed object. In the Beaufort, where the coast is nearly parallel to the wind direction, we can have a front come through easterly to westerly or westerly to easterly wind change. And we've seen pileups or ride-ups with both. But we tend to have more when we go from easterly to westerly because we go from a water level set down to a setup. With storm surge, we release the ice that may be grounded near shore, and it can more easily move on shore. In the Chukchi, it's pretty much unidirectional. Now the coast is nearly parallel to the predominant wind, perpendicular to the predominant wind direction. So we need an easterly or offshore wind followed abruptly by a westerly or onshore wind to promote pileups and ride-ups. Secondary considerations, if we have these first two criteria fulfilled, the characteristics of the ice itself. We see almost exclusively pileups during freeze-up when the ice is thin and weak and brittle. We still have to have about 15 to 20 centimeters minimum, or the pileups don't amount to anything. In between about 20 centimeters and 40 centimeters is the sweet spot for seeing pileups during freeze-up. We have a quiescent period in midwinter when the ice is thick and strong, doesn't move much, maybe tens of meters, even in the case of landfast ice. And finally, we see both pileups and ride-ups during breakup when the ice is thick, but it's weak and ductile. And all other things being equal, the degree of exposure is important. If we have an exposed site with no coastal protection or outside of a lagoonal area, we tend to get more frequent ride-ups and pileups with a higher degree of severity than we would in a semi-protected environment, such as a place like Harrison Bay. In terms of seasonality, based upon the observations that we'll go into in a few moments, during freeze-up, we see pileups forming from early October to early December, about 2 months, when we have that sweet spot for ice thicknesses I mentioned a moment ago. 30 centimeters is about what we often see in terms of these pileup block thicknesses. At exposed locations from mid-October to mid-January, a period of about 3 months, and recall that on North Star Island, that occurred at near the end of this period on January 8th. Breakup, it's a far shorter period, only about 2 to 3 weeks at both sheltered and exposed locations. Its breakup is far shorter than freeze-up as a season, and similarly with the formation of encroachment events, it's really late June to early July. In the Chukchi, we have less information, but what we've seen so far, we can see ride-ups and pileups forming late October to early January, about 2.5 months, and breakup, even more limited data. We see ride-ups and pileups from late May until early July, about 1.5 months. A little longer season at breakup in the Chukchi. I'd like to turn now to historical data that we have, which I was surprised when I became involved with Ken Vaudry in this field that we have much more data than I anticipated. And we tried to summarize this in 2012 in a report prepared for Bessie and Shell. You see here known as ice encroachment in the Alaskan Beaufort Sea. This is available from Bessie. It's in the public domain. And we included tabular summaries of the events that occurred over a 29-year period from 73 to 2011. And as you can see, we segregated the data into 6 categories: pileups on both sheltered and exposed man-made facilities, pileups on sheltered and exposed natural shorelines, and ride-ups on sheltered and exposed natural shorelines. And you see our population's not bad here. We have from 25 to 45 events in each of these categories. The obvious omission here is ride-ups on man-made facilities because we don't see any. Typically, either the roughness of the man-made shoreline and or its inclination tend to promote pileups rather than ride-ups. And so we really don't have any events here to categorize. Here's an example of the historical information that's tabulated, and we'll come back to this again in a few minutes, but we try to categorize them by the year in which they occurred and the date, which correlates with, on the right-hand 2 columns, the weather conditions. We've tried to document water depth and side slope, and then the characteristics of the pileup itself, block thickness, the maximum pileup elevation and the encroachment, and if there were a work surface, how much we encroach onto it. Second source of historical data I would point you to is really started in 2009-10 and has continued to the present. This again is work performed with Ken Vaudry for Bessie and Shell, and we performed annual freeze up and breakup studies, freeze up for 13 years, as you can see here, and breakup for 6 years, 2017 and 2020 through the present. And in each of these, we've flown nearshore reconnaissance flights at the end of the freeze-up period and more recently near the end of the breakup period. And while the data here are not significant for you, you can see this PU or pileup designation, 4 meters high, 7 meters encroachment. We've documented these by location and by features and then tabulated them on, you see on the right, where they occurred, when they occurred, based upon an assessment of the environmental conditions, the 15 knots and the abrupt wind change, the direction from which they arrived, and then the characteristics of the pileup itself. Bessie is currently contemplating, and we're strongly urging them to present these data. I think they're ideal for a GIS portal, where we've just shown an example here on the northern Chukchi Sea coast, where we have sufficient information, particularly during freeze up now, to create a heat map, if you will, of where encroachment occurs and to what degree we have to be aware of it. Each of these boxes indicates the number of pileups per kilometer per decade, along with the maximum characteristics we've observed during the period of record. And we're starting to get sufficient data to break this into 1 kilometer segments, where now we can look, it's kind of like an erosion map by kilometer. Here it's an encroachment map by kilometer. So if you had discretion in siting a facility, maybe a cable crossing, you would look for example, the white zone here and not the bright red one. And finally, our almost laughable but best effort attempt at predicting these events. It's a very stochastic process. It's so random, and the ice is such a difficult material to model. Our experience has been, although a number of people have made valiant attempts, both physical and numerical modeling have come up short in terms of producing reliable results that can be used for design purposes. In terms of write-ups, so we have no predictive methodology, and I think the best we can do is a first order estimate of the write-up potential from historical events at sites with similar exposure. Go back to those tables we looked at a few moments ago, particularly if it's in geographic proximity to the site of interest. Fortunately, as I mentioned, write-ups tend not to occur on man-made shorelines or structures, docks, islands, and so forth. And so this is probably not as critical as an absence of a predictive method as we might expect. And in terms of pileups, where we have more information, we have used statistical extrapolation of historical pileups and the site geometry to come up with a design pileup height and then design encroachment distance. And we'll walk through the process, but it really consists of 4 steps. Select historical events that occurred under similar circumstances, and all things being equal, we prefer geographic proximity because we don't understand the driving forces behind these things very well. Then to perform an extremal analysis to estimate pileup elevation for the desired return period, say 100 years in many cases for a permanent structure. The leap of faith here we'll look at in a moment is to estimate the geometry of the pileup. And then once we have that, we can compute the encroachment based on the site geometry. So let's just quickly go through it. The details are not important. I'd just like to acquaint you with the method. This is that table we looked at earlier, and we might pick perhaps 10 or 12 events here in similar water depths, maybe similar side slopes, hopefully close to our site, that are representative, we think, of the conditions we're facing. Do a probability of non-exceedance, and from that we can get predicted 100-year return period. For example, here would be about 11 meters under these circumstances. Here's the leap of faith. We have to somehow pin down the geometry of the pileup, and as you probably saw from those earlier photos, it's quite variable, but experientially, 2 things we need to compute the encroachment. One is the angle of repose on the backside of the pileup, this angle beta. And it tends to be, not always, but it tends to be greater than or equal to 30 degrees. And so the greatest encroachment results from a 30-degree angle of repose. So we typically assume that. The other difficult parameter to define even more so is the location of the pileup peak relative to the water line or the structure. And what we found, again, experientially, is that in relatively semi-protected or quiescent conditions, the pileup peak tends to occur more offshore. Conservatively, we might say at the waterline. In moderate exposure, it might occur over a break and slope, as you see here, where this is shown in this particular graphic. And in a very extreme environment, we might see the pileup peak well inland. For discussion purposes, we assume it might be at the edge of the work surface, the area where facilities of interest are located. So we're assuming that this pileup peak, we might try several iterations, but it's somewhere between the water line and the area where we have to protect. Once we have that, it's just basically geometry. We have H, the pileup height, which we got from the extremal analysis. We know the height of the work surface, capital H. We've assumed beta, and we've assumed L, and then we can compute the total encroachment from the water line to the innermost or landwardmost projection of the ice. And then the work surface encroachment for design purposes is simply the total encroachment minus the distance from the water line to the structure edge. And recall, over the design life of a structure, kind of in line with what Emily implied earlier, if we're on an eroding coast, we have to first take into account the erosion over the life of the facility. Say it's 1 meter per year per 20 years, and set back that far, and then add the encroachment allowance or buffer zone behind that. So, your turn. Thank you for your attention and your interest.
Great. Thanks so much, Craig. So opening it up for questions for Craig, but also for questions for both of our speakers today. I know that Tom might have some questions, but other folks too are welcome to chime in.
Well, since no one's jumping up, Craig, excellent presentation, and Emily's presentation was also excellent. Thank you. I'm kind of curious if you see an effect of climate change on your observations or in your thinking.
Are you asking both of us, Tom, or
well, you right now? Yeah, thank you.
I was afraid someone would ask that, and thank you for doing so. The most honest answer I can give you is we have insufficient information to really discern a change. We're still in the primitive stage of learning the letters and the syllables, and we don't speak the language of encroachment very well yet. That said, we have not seen a distinct change so far. In fact, if you notice, many of the pictures that I showed in the presentation are from about a decade ago, from 5 to 10 years ago. And in the last 5 or so years, we haven't seen a commensurate increase in the frequency or the severity of these pileup and encroachment events. We also thought we would see an increase, for example, in ice drift, right? That in these freeze-up studies, we're looking at, we have thinner first-year ice, we have less multi-year ice, the ice canopy is less competent, we have higher temperatures, weaker ice. All these would, we think, contribute to a more mobile ice pack, probably greater ridge formation and greater drift speeds as well. And we haven't seen it. We're still seeing about 5 to 6 nautical miles per day, which surprises us. So I suspect that we're just ignorant of the nuances here. We are seeing changes in other parameters. The one that's most shocking to me is just since we began our study in 2910, we've looked at the dates, a trend in the dates of nearshore freeze-up. This is the area out to what that Emily mentioned, basically the area covered by landfast ice, about the 20-meter isobath. And we have seen that slip by about 3 days per year on trend in both the Beaufort and the Chukchi. That's pretty shocking. That means since we've been doing this, we've delayed nearshore freeze-up by a month. So we see trends in other areas, but to answer more succinctly, I don't think we know enough. We've not seen a trend in terms of encroachment severity or frequency.
but the timing might be changed a little bit.
Definitely. Actually, another interesting, stop me if I'm too deep here, but we found that freeze up is definitely migrating later and is taking longer to occur. The duration of freeze up from first ice to complete cover of the basin is increasing as well. Breakup is changing much less rapidly. We're seeing probably an order of magnitude less change, though we have fewer data points here. I think what we're seeing is it's this effect of the positive feedback loop. When we have less ice in the fall, we heat the water faster, we heat the air faster, we melt more ice, we have less ice. And so it's really spiraling downward at a rapid rate. So freeze up is changing rapidly. Breakup is changing very slowly, I think, because the ice canopy, whether it's 5 feet or 5.5 feet thick, it's still there, still insulating the ocean. So we see some changes, but surprisingly slow at breakup.
Rob, I see you've come on and your hand's up.
Yeah. First, I'd like to introduce myself. I'm new to the group here. As I said in chat, I'm at Sandia National Labs, and somebody sent me, Jennifer Frederick sent me a message that this was going on, that there's going to be some ice scouring talk today. So I was very happy to see that. It was a very excellent talk. So just coincidentally, last week I gave a talk at GSA on detecting ice scours in real time using distributed acoustic sensing on the fiber that that Emily was showing. So I would be happy to give a talk maybe at the next meeting or something if you guys want to see that. I think it's pretty interesting things. I'm a tourist in the cryosphere, so I'm mostly just a solid earth geophysicist. So to be patient with me perhaps, but we also do some very interesting things with sea ice extent and sea ice thickness and ice quakes and stuff like that as well. And that could be topics for further discussion. But yeah, let me know when the next meeting is, and I'll try to see if I can be available for a talk.
Yeah, thanks, Rob. I'll be sure to follow up with you. So you said that you use the cable off of a lick talk?
Yes. Yeah, and in fact we're still using it. So we have continuous monitoring right now for this year and next year.
I wonder if your data could get at some of that scour rate question that Emily
Yeah,
talked about.
that was the plan actually. Yeah, so you have these scours, you don't know how long they've been there, how fast they erode. So one way to determine how fast it erodes is determine, well, statistically, how often do they happen, and kind of work back from there. So that was kind of one of the main motivators for the study. Right now, we just did a pilot study, so to speak, and just to see if it would work, and it seems to be working pretty well. Jessica Ertz, who's also at Sandia, she's a new career staff at Sandia. She'll be taking up the mantle for this next year and moving forward with it.
Yeah, very cool. I'll be sure to follow up with you about presenting on some of this. Steve Dykstra, I see that your camera is on. Did you have a question?
Yeah, I have a bunch of questions, but
You have 1 minute.
All right, I'll quiz Emily later about hers. So Craig, I'm wondering about the mechanics of these events and what's creating them. Could you elaborate a little bit more on the wind directions and the setup set down dynamics, how that might relate to Ekman dynamics as you're thinking about wind directions? You just talked about east-west winds, but occasionally winds can be strong from other directions too. So any insights there?
I'll try. I haven't organized it carefully in my brain, but let's go through it. Key point, Coriolis back to high school physics is proportional to the sign of the latitude. So at 70 degrees north, we have a very strong Coriolis effect. In the Beaufort Sea, we tend to have coast parallel winds. Easterly is a slight onshore component, westerly is a slight offshore component, based upon the east, southeast, west, northwest orientation of the coastline. Okay, so what happens then if we have an easterly, it's pulling the water to the right offshore. If anything, we're grounding the ice more firmly against the sea bottom if it's close already. And so we can still break it loose if there's sufficient momentum, but it tends, if anything, to resist displacement. Whereas in the westerly, we now have the converse. We have the wind is blowing the ice to the east. It turns to its right. The water turns to its right. We have setup, which can be in any given summer, 2 or 3 feet, probably in the winter, half of that because of the damping of the ice canopy, maybe a couple of feet. But that's enough to break the ice keels loose from the bottom. And so if anything, we see I can't quantify it, but we see perhaps higher frequency of large pileup and ride-up events from the westerly events. But the key here that this, I was totally ignorant of this until Ken Vaudry started to look at it, and then we looked at it together. It's really the change in wind direction. It's the momentum change that we need, that the ice is literally leaning left, if you will, and then suddenly this can't happen over days. It's like hours. You know, within a day we have a shift. A front goes by, typically one of these tightly wound low pressure systems passes by. We go from one direction to the other, wind change of maybe 150 degrees. And then we have this momentum gathering, and that's what kicks it loose. And again, in the Chukchi, the wind tends to be more onshore, offshore. And so it really takes the easterly blowing it away and creating a flaw lead, which can be a massive expanse of water. And then if the wind shifts to westerly and onshore, here it's not so much Coriolis, it's just brute force that we have the wind. Now, the wind drag on the ice blows it onshore, and there's typically not sufficient time or space for it to turn so much. It just comes onshore. And so we got, for example, that massive pileup at Skull Cliff that we looked at earlier. Does that help a bit? It really, in the Beaufort, it's really related to Coriolis and latitude, but we can have from any direction, and almost all of our storms have a northeasterly, east-northeasterly, south-southwesterly bias based on the windroses we've accumulated in the last decade or so. So you tend to see this coast parallel wind, and then it can shift from any direction to another direction, almost omnidirectional shifting, as long as it's 15 knots and as long as it changes abruptly.
Sure. But yeah, I'm curious too about the Ekman dynamics there. So if you're thinking about the setup set down being driven by the east-west winds on the Beaufort, like do you have to have open water then? Because otherwise, if it's just wind shear on the ice, you wouldn't have fully developed Ekman dynamics.
You wouldn't, but remember, we're just dealing with the surface here. All of this, we're not looking at multi-year ice keels here.
Sure.
We're looking at the stuff that's, it's during freeze up, it's 20, 30, 40 centimeters thick. So you're really looking at just the surface transport here. And what we found rather surprisingly, if you look at water levels, measure water levels during the period when the ice canopy is in place, you still see significant setup and set down. It's rather shocking. For example, some of the ice roads that are constructed typically between January and March to support offshore construction in April, May, June, when you have a thick enough road to drive on it, those have been disrupted by particularly westerlies that cause the water to rise, crack the ice, and then flood the ice surface. So I can't understand it. Maybe there's enough slack in the canopy that it seems to respond, albeit damp, but it nevertheless responds quite significantly to changes in wind direction.
Okay. Yeah. How much is it based on the change in the atmospheric pressure versus the wind stress?
Good question. I think atmospheric barometer effect is important, particularly for storm surge. I mean, we always try to be sure that's considered in this assessment. It's Coriolis, but it's also atmospheric changes, and this inverted barometer effect helps with the surge events. I think it's probably a lesser magnitude than the wind conditions, but there may be a codependency here that we tend to get wind with significant pressure changes. I haven't seen it. I would think that the wind is far more important than the pressure effect here, as a first approximation.
Okay, thanks.
Well, Craig, we have a question in the chat. Considering these physical processes, ice ride-up, pileup, and encroachment, which do you think are most critical for ports in Alaska? there's interest in how these processes might affect maritime operations near ports now and in the future.
Well, I would start, first of all, we're primarily looking at Arctic, right? As opposed to some of the ports proposed for Western Alaska that would be feeder ports, if you will, or logistics bases. It's a different ice environment, and I don't know to the extent that encroachment is important there, but I would expect less because the ice tends to be quite a bit thinner and weaker by virtue of the temperature. Although I don't think it can't be ignored, but I think if we restrict our attention to the Arctic, I'd go back to a comment I made earlier first, that ice loading is far more important for port structures. I mean, looking at a LNG terminal or looking at a dock, for example, projecting out past the very nearshore area, the loads are tremendous. You know, there's a reason there are no pile-founded structures in this environment, that the loads are just enormous. And so if you can design a structure and construct something that will withstand the ice loads, you probably will be okay for encroachment as long as you provide a setback distance, a buffer zone around it. So I think it's still necessary to compute this phenomenon. And I didn't mention these events tend to occur it's not a lightning bolt, but it tends to occur over a period of minutes or tens of minutes as opposed to hours or days when we have these encroachment events. So there is, if you have an event that, let's say, covers a dock or something that is of non-critical environmental importance or not crucial to human life, you can clear it and you can resume operations in the port. For example, on Prudhoe Bay West Dock, there have been several occasions when ice has overridden. You get mechanical excavation equipment out, or on North Star, we saw you clear it and you go on with life, as long as you don't have critical facilities in harm's way. So that's where the seasonality is important, to stay out of harm's way during those freeze up breakup seasons. And then a warning system, if you have, let's say, a oil tank or a crane or something in an exposed location, and you see a front coming through with winds over 15 knots, it's probably a good time to get those out of the way. So I think it's manageable and far less severe, but nonetheless, it is an important, but not the primary consideration for a port.
Thanks, Craig. Okay, so I think we'll, if you guys have time, we'll take Anne's question and then Bessie's question. And then we'll end it there. So go ahead, Anne.
Okay. I was just thinking, have you talked to, for example, whaling captains, folks who spend a lot of time on the ice, about these events? Because this is something they have to think about and be aware of. I mean, they spend time camped on the ice. You know, I know stories where literally people have taken scientists out. Scientists didn't want to leave. They want, you know, the guy says, no, we got to go now because we are going to have an ice override event, you know. And within 10, the guy they left their equipment because he managed to scare him enough. And so they eventually retrieved it. And literally it goes from, you have open water with a tiny little line of ice on the horizon to the camera being upended by the ice coming in within less than 10 minutes. But they knew it was coming, is the point. So you might get a lot of really useful data about what's going on, because they're not just, you know, getting this through intuition. So have you tried doing that?
We have talked with a number of residents, particularly Utqiagvik, as well as communities both south, like Wainwright and Barter Island. And we find that their information on EVU, you know, the ice tend to be right up, and historical damage to communities is very real and very helpful as a background. Because it's not quantitative, it's difficult to blend that into, other than be an awareness of where sites are vulnerable and what's the magnitude of the events. It's difficult to quantify those observations. You know, as a mariner, you kind of get an idea of what's important and what's not, but you don't quantify it the way that a scientific or an engineering person might. So I would say it's very useful background. We do avail ourselves of local knowledge and try to use that as the foundation on which to build a more quantitative understanding.
So my experience with trying to elicit more shall we say, solid numerically useful data from that is sometimes setting up various scenarios, and asking everybody about, can be very helpful, because then you start to get, no, that's, I wouldn't be worried. I'd just be sitting on the ice, I'd be happy sitting on the ice, not too worried about it, or, I'd be out of there, kind of thing. And so you might be able to get at least not precise numbers, but stuff that you could then go back and, there's a lot of Weather Service records, particularly Utqiagvik, but some of the other places have, some data. So you might be able to start pulling stuff out of there, patterns, not hard engineering data, but patterns. And that makes it easier to look, and
Right.
being predictive. Because, they're pretty darn good at predicting when it's going to happen.
We've also found assets in people who are kind of comfortable in both worlds, like Richard Glenn at Utqiagvik, who has a somewhat quantitative understanding of the environment as well as experiential. And so he is oftentimes, for example, a consolidator when we had information on ice islands arriving from Canada and their point of origin and the rocks that were on them and where they might have caused gouging of the seafloor. Someone like that who is comfortable in both worlds has been an extreme asset to us as kind of a funnel into information we otherwise wouldn't get.
Bessie, go ahead.
Thank you. Hi, Bessie Weston. I'm out on Nunivak Island, Macquarie, Alaska. So I just want, and thank you so much for bringing up that question, because that was exactly what I was going to ask. But with the addition of knowing that big oil has been exploring up there forever, well, to me, forever. Have you not been able to look back at their data, or is their data just not available to you?
A lot of those are the data that I presented today to a large extent. Okay, all of those facilities were actually monitored on behalf of either Department of the Interior or the oil industry, or both. And so actually we do have access to, and I think what you saw today is a compilation of the best information available from those sources. So they've been very forthcoming. I particularly thank Shell for making everything available in the public domain, and Bessie and Department of the Interior has continued that research since primarily the exit of the forward-looking oil companies in around 2015, 2016. But I think the data that you saw, all those, the table, for example, on events on man-made facilities, those are largely oil facilities.
Okay, thank you. I mean, I realized that those were oil facilities. I didn't realize that the organizations that you were working with or that must have been contractors, sounds like it. But on that note, my internet is spotty because I'm rural Alaska. Did I miss any credits to the locals that provided information that might have given you any history or knowledge with the data that you were able to provide?
You did not, because I didn't show any data directly derived from those people. As I mentioned, it's not to belittle or discredit folks with whom we talked. Their information was foundational to understand how this was of concern to the community and how it might have been impactful in the past. The quantitative findings were all from dedicated studies contracted for either by private companies in the oil industry or by Department of the Interior. So as I mentioned, the traditional knowledge that we became familiar with was very much appreciated and kind of formed a foundation that allowed us to understand more the specific details that we got from the more recent observations on man-made facilities and natural shorelines.
Thank you.
Thank you.
Okay, great. Thank you both so much for answering all those questions and for staying over. It was great to have this discussion at the end, so really appreciate that. Thank you again to our speakers. Thank you to everyone who is still on this call, who's stuck around for this discussion. And we'll see you next time. Take care.
Thank you.
Thanks, everyone.